Hi there guys, welcome to this video on a proof, and in this video we're going to look particularly when we've got these inequalities. So if this was an equals, we normally set up like left hand side is identically equal to, we try and work that through to equal the right hand side or vice versa. But this is slightly more complicated, and what I'm always going to do to start off with is something called our jottings. Now I'm going to write the word jottings down here. And this isn't going to ever be looked at by an examiner, and if I just carry on, I'll tell you why I've done this once we reach a significant point. So we're given that a is a positive real number, and that's really important because if I'm multiplying or dividing by negatives, obviously this is going to change direction. So the fact that it's positive, I can freely multiply by this and not have to worry too much about this sign. So if I multiply, I get a squared multiplied by a, to both sides, plus 1 is greater than or equal to 2a, and you'll want to get all that on one side naturally, so let's do that. So I've got a quadratic, and I'm going to want to factorize that. And what we've done here, by doing these jottings, I've arrived at a fact that I know is true. And always true, no matter what value of a I put in there, this is true, and we call that a true axiom. Yeah, it's a fact that is, always true. So the reason for the jottings is we actually start our proof with an axiom. That's what we have to start from. Now, so just doing that provides us with the axiom. So this is actually where we're going to start. So I'm going to rewrite that. Now what we've got to do is try to prove this. So let's have a little think about what we can do here. So if I expand that, so quite often a lot of it will be just undoing what you just did on your jottings. And you can see here that I could, so we're trying to get it back to there now. So what would we do here? So if I divide by a, I would get that, yeah, a squared divided by a, 2a divided by a. And the reason I can do this, this works, you don't have to say this, because we know a is, and I'm just going to write positive like that, it's a bit of a shortcut. Now if we didn't know it was negative, then this isn't true, but because a is positive, we can definitely do that, and therefore we can say a plus 1 over a is more than or equal to 2. So that's proven, but you can only start your proof from an axiom, and then you can manipulate it to get what you want it to. So that one is kind of dull because it is really the opposite of what we've just done. So let's have a look at another one. So here we've got to prove that for all real values of x, this. So I'm going to start with my jottings. And this won't receive any, no one's going to mark your jottings, okay, even if you don't write the word, because it's not starting from an axiom, so this isn't part of your proof. So I would go ahead and just, for your own benefit, write the word jottings. Now, and looking at that, the only thing I can think of doing is expanding it. So that's what I'm going to do. So x squared plus 12x plus 36 is going to be greater than or equal to 2x plus 11. Now naturally I want to bring everything on one side, and at this point you start to see that if you factorize this, you're going to get x plus 5 all squared is equal to 0, and that there is our axiom, our true undeniable fact that we can start our proof from. So let's start our proof with the axiom. So from here, the only thing you can do is expand. So if we expand this out, and then it's pretty hard now to get back to here. So what you want to try and think is, well, what is this equal to? We know that is equal to this, and this is equal to that plus this. Okay, so this is the connection we're trying to make. So we can see that this is equal to that plus that. So I can say x plus 5 all squared plus 2x plus 11. So I can do that from my axiom at the start here. Now, because we're at, well, we've got, let's put that in brackets as well for now. So we've got 2x plus 11 plus something is equal to that. So it means that if this was equal to 0, for example, when x is minus 5, that would be 0, then these two things must be equal to each other. So we've proven that it's equal. But if that is not minus 5, it's going to be a positive because it's being squared. So that plus something must equal this. So therefore, it must also be more than this. So therefore, we can say x plus 6 all squared must be bigger than or equal to 2x at 11, because we're adding something on to 2x plus 11 to get this value. So that's a bit of a more interesting one to look at. Let's do one more. So again, we've got all positive values of x and y. We have to prove this. So I'm going to start with my jottings, and the only thing I can really think of doing here is making the denominators the same. So you get x squared plus y squared all over xy, and that is greater than 2. Let's multiply by xy. So we get x squared plus y squared is greater than 2xy. Let's bring it all over one side. Now this is possibly a harder factorizing problem to see, but it is as simple as x minus y all squared. And that, ladies and gents, is an axiom. That's always true. So now we can start our proof, and we'll start with that. And now we've just got to get back to this. We've got to basically prove that fact. So x squared minus 2xy plus y squared, and this is really similar to the first one because I can just now divide by, it's up to you how you want to do this. You could divide by x or xy or just y, and take a few stages to get there. But if we divide by xy, what we're actually going to have is that. And the reason we can do that is because xy is positive, because we know up here that we've been told they're positive. And if they were negative, then this isn't a good enough stage of working, because we'd have to change the direction of the inequality sign. So therefore we can say x over y plus y over x must be greater than or equal to 2. So the middle one is the more exciting example, the harder one. The first one and the last one is just basically I'm undoing my proof, my jotting, sorry. But you must always start your proof from an axiom, and that's the trick.